Welcome to the third presentation in Unit 3 entitled It's All About Potential. It says not everyone gets to be a bounty hunter when they grow up. So the learning goals for this particular presentation are that students be able to identify if an object has kinetic or potential energy and describe. Welcome to the third presentation in Unit 3 entitled It's All About Potential. It says potential, not everyone gets to be a bounty hunter when they grow up. So the learning goals for this particular presentation are that students be able to identify if an object has kinetic or potential energy, describe the transformation between potential and kinetic, and distinguish between the various types of potential energy. So here's what we already know. We already know that work is a type of energy that's measured in joules, and that power is the rate at which energy is used, and that energy must be converted between the different forms. So here's what we learned in the lab. Objects can have potential energy, and we think of potential energy as stored energy. We know that objects can have kinetic energy, and kinetic energy is the energy of movement. So when you were firing the rubber bands, okay, at one point they had potential and another point they had kinetic, so that energy can be transferred between the two. We know that potential energy can store energy in many different forms. Objects can have above the surface of the earth have gravitational potential energy. That's why we see gravity, it's just a theory. So you see the another example of that is if you take a look at the work equation. If you were to move an object up vertically, you're doing work in lifting the object up. Well, when you stop lifting the object up, that energy has to go somewhere. And where that energy is it's stored in its position relative to the earth. In other words, the box can lose that energy as it falls down. You have gravitational potential energy. The more massive the object, the more gravitational potential energy. The reason being, the more work it requires to lift it. The greater the height, the more GPE, because once again, the more work done in lifting it. And then finally, the greater the gravity, the more GPE there is, the more gravitational potential. Now, gravity is a constant on Earth, so whenever we look at things that are on Earth, we can compare them just based on mass and how high they are. But if you're comparing something on Jupiter to, say, something on the moon, you can't make that assumption anymore. Finally, we have elastic potential energy. It says the more an object is stretched, so the more you pull it back, the more elastic potential energy it has. And then the more difficult the rubber band is to stretch. If you have a really thick rubber band, it takes more energy to stretch that thing out, the more energy is stored in the band itself. So it says potential energy is a unit of energy. What should the units be reported in? All energy is measured in joules. So it says which box has a greater gravitational potential energy. We're going to assume this is the ground right here. So if you look, this is the height of the first box. This is the height of the second box. And assuming these two boxes are the same, which it looks like they are, then we can say that the one with the greater height is. So we would say that this is a greater height. So we would say this box has the greatest gravitational potential energy. It says each rubber band below is stretched 5 centimeters, which has the most energy stored in it. It's a little bit difficult to tell, but all these rubber bands right here have a different thickness. And this pink one right here actually has the greatest thickness of all of them. So because of that, the pink one is going to have the most energy stored in it because it's going to be the most difficult one to stretch. Finally, we have a mastery level question. It says the gravitational potential energy can be calculated using the formula GPE, which is for gravitational potential energy, is equal to mgh, where you have mass, gravity, and height. So it says, what is the gravitational potential energy of a 2 kilogram book 10 meters above the surface of the Earth, where gravity is 9.8? So we have mass is equal to 2 kilograms. We have gravity is 9.8 meters per second squared, and we have our height as 10 meters. At that point, we can plug it into the equation that's already written. We can say equals 2 9.8 times 10. When you multiply all those things out, you end up getting something on the order of 196, and then our unit is the joule. Next, we need to talk about kinetic energy. Kinetic energy is defined as the energy of movement. So whenever something moves, and everything generally moves, it's going to have some sort of kinetic energy. Now, the greater the mass, the more kinetic energy, and the greater the velocity, the more kinetic energy. Something like a car moving at 60 miles an hour is going to have more kinetic energy than something like a cloud moving at 60 miles per hour. And whenever you have something like a car moving at 100 miles per hour, it's going to have more kinetic energy than a car moving at 20 miles per hour. So, kinetic energy is a unit of energy. What should the units be reported in? And that is, of course, the joules, just like it is for all energies. It says which object below will have the greatest kinetic energy, assuming they are moving at the same velocity. So, unless the pictures are just totally out of whack, this dump truck clearly has more mass than the sports car. So, because of that, this has smaller mass. So, the more mass, the more kinetic energy, as long as they have the same velocity. And this one, it says a pitcher throws a baseball at 40 meters per second, 2 meters above the ground, while the second remains at rest 3 meters above the ground. Which one has the greatest kinetic energy? Well, remember, kinetic energy is related to how fast the ball is moving. So while this one is at rest, it has zero kinetic energy. So this one right here, even though it's going to have quite a bit of kinetic energy, if it's moving at all, will have more kinetic energy than the second. So because of that, we can say the ball moving at 40 meters per second is going to have more kinetic energy. Finally, it says kinetic energy can be calculated using the formula below. How much kinetic energy does a 1,000 kilogram car moving at 20 meters per second have? So you would say, okay, this is my mass, this is my velocity, and I would plug in. I would say 1/2 the mass, which is 1,000, times my velocity, which is 20, and that 20 is squared. So at this point, I would get my calculator, and I would say 1/2 or 0.5 times 1,000 times 20 squared, and that ends up giving me a value of about 200,000 joules. So we'll say 200,000 joules.